Okay, so this is the last and I guess most advanced part of vibrational spectroscopy is looking at some of the other signals that show up in the spectrum. So we're doing gas phase spectroscopy still, so we're going to see PNR branches, but there are some things that may be confusing to us. Like when we look at this automobile exhaust spectrum, we see the fundamentals for carbon dioxide here, right? So this is 001 here. This is the symmetric stretch of CO2. Oh, asymmetric. Put an A in front of that. The symmetric stretch is Raman active. Okay, so how many vibrations should CO2 have? We've identified 2 of them. So what's the formula for vibrations? How number of vibrations in a molecule? I've heard a couple of answers which are both right in different contexts, 3n minus 6 and 3n minus 5. And so which is it for CO2? Excellent, because it's a linear molecule. So we lose one of the rotations, which means we have a smaller minus. All right, the minus part is minusing the translations. There's 3 of those. And in a nonlinear molecule, there's 3 rotations. And so that adds up to 6. We're taking those out, and the rest is vibrations. The 3n is the total number of things a molecule can do. Every atom can move in 3 directions. And so if you have n atoms, you have 3 times that number of possibilities. 3 of those are translations. 3 of those are rotations if it's nonlinear. But if it's linear, the rotation around the z-axis is not defined. And so then we can't count that one as a rotation. So that's why it's 3n minus 5. So for CO2, 3n is, 3 times 3 is 9, okay? And so then we subtract 5, the 3 translations, the 2 rotations, and we're left with 4 vibrations. We've identified 2 of them, the symmetric stretch and the asymmetric stretch. And we have this peak down here, this CO2, this new 2 here. That's the bend. And so we're going to draw this molecule over here on the side. And we have the coordinate system with Z going up and down, X coming out, and Y going to the side. And this bending motion can occur in the Y direction, where the oxygens go left and the carbon goes right. And that's in the ZY plane, but it could also come front and back into the XZ plane. And so it could also be like this. So since there are 2 different directions it can bend, that counts for the 2 bends. So it can come, this carbon can come forward while those oxygens go back. I'm drawing these arrows diagonally to line up with that x-axis. So they're meant to go in the x direction. So the carbon's coming forward in x and the 2 oxygens are going back, and sometime later they'll all switch directions. And so that's the, I guess, let's see, normally so if my head is the carbon and my oxygens are here and here, it's like this, okay, right? Or back and front. I'm choking myself. So those are the 2 bends. And so there's our 4 vibrations. Even though this one is at the same frequency, it's an E mode. So in the Millikan notation, it's E, and that's doubly degenerate. So they have the same energy, which means they show up at the same frequency. So this one is labeled E, because it contains both these vibrations. The symmetric stretch is going to be A1G, and the asymmetric stretch is A1U. Morning. But if we were to look at CO2, if we add in more CO2 or take out CO2, we see some other peaks grow and shrink with the partial pressure of CO2. So we know they're related to CO2. And that's these combination bands here. So that's what today's discussion is understanding these combination bands of CO2. We know they're related to CO2 because they track with the partial pressure of CO2. We put more in there, they get taller. We take it out, they get less. And so let's understand what's going on with these combination bands. Now, what's all of this business on the x-axis? Well, this is, again, just showing you how this is related to quantum mechanics. This is the wave functions, the Schrodinger equation, and the Hamiltonian. And so we have the lower state energies here, and this would be the energies of the ground state, so 0, 0, 0, the Hamiltonian. So these are the wave functions with these quantum numbers. And so this would be the ground state energies. These would be the excited state energies. And notice there's a lot of redundancy here. There's lots of zeros and V primes. And so we could just label these with the only thing that's different, and that is the V primes. But my point is that the wave functions and the Hamiltonian are still here in the spectrum. It's just that x-axis is the difference between the energies. That's the transition equation, okay? Not the transition dipole moment integral, the transition equation. That tells us where these peaks show up in the spectrum. You know, like 667 wave numbers is the difference between those energy levels. And this is 2350. And so that's those wavelengths, or in this case, wave number values, come from the transition equation, which is the difference between the energies for these transitions. Now, these three are fundamentals. You see, they just have a single excitation in one of those quantum states. So these three are fundamentals, and a fundamental is different than a combination band. A combination band has got multiple changes in quantum numbers. It starts at 0, 0, 0, but it goes up, say, 1 unit here and 2 units there in different vibrations. So let's look at what those fundamentals are. So here's the CO2 stretches. So the asymmetric stretch is on top and the symmetric stretch is on bottom. And what makes it asymmetric or symmetric? The symmetric stretch, we're using the word symmetry here to talk about how the bonds are stretching. And if they're stretching together, both bonds are increasing at the same time, we call that symmetric. Okay, so it's a slightly different use of the word symmetric. We're not talking about the character table here. We're just talking about, are both bonds increasing at the same time, or is one increasing while the other one is decreasing? So the top one is asymmetric because one bond is stretching while the other one is shrinking, and vice versa. We could look at these and compare them to the coordinate system. And if we could take a snapshot, we could see that there's an oscillating dipole along the z-axis. And so since that oscillating dipole is along the z-axis, this particular frequency has z Cartesian symmetry, and that means that it's A1G. Since these are the same in z, plus and minus z, that looks like z squared. Because again, if you square the z-axis, then all the negative numbers become positive. So in both directions, it's the same. You can think of it as both bond lengths are increasing on both ends of the z-axis, so they both have positive values. So that's why we say if you can identify the z-axis, and if it's the same in positive z as it is in negative z, then that's going to behave like z squared. So we go down to the character table, we find z squared, and that's going to be A1G. I think I screwed up the top one. Yeah, I just said A1G, but that's really A1U. So let me scratch that out. So you go down here in the character table and find Z, and it's A1U. So forgive me for that mistake. Minus 3 points. Okay. And I'm just showing you the Raman and the IR arrow diagrams. Just again, that's the energy level diagram that you can see there. So let's think about the combination bands now. This is quite a bit different. So we have shown here the nu 2 vibration, which is roughly 700. It's like 670 wave numbers. So we'll just say 700 wave numbers. And so this is the IR active mode. Let's see, which one is it? It's nu, IR active is nu 3. Okay. And then nu 1 was the Raman mode. But way down here in energy is the nu 2 mode, 700 wave numbers. And you see all of these start in the ground state of 0, 0, 0. And they're all fundamentals. All three of these are fundamental transitions. But there is this combination band. If we were to figure out how to get to 3684, one of the possibilities is to have 2 times 700 plus I've got it right here, plus the 2300 of nu 1, and that gets us to 3700. And so this is where combination bands get difficult, and I'm not going to have you do this. We're really just identifying why the combination bands that we observe are there, but it's pretty tricky when you find a peak in the spectrum that you know, like this case, is related to CO2, to try to figure out what vibrational modes are adding up to that. Now, you can do it in CO2 because it's only got 3 vibrations, and so you got to figure out how, with these 3 numbers, am I going to get to 3700 wave numbers. And so 2700 or 2300 gets us close. Adding in 700 gets us to 3000, and that we still need more, so we need another 700. Well, we've got a vibration at 700, so add in another one of those, and that gets us to 3700. And so it's just like a puzzle, trying to figure out which types of vibrations will add up to this total that we see in the spectrum. So this is just this is nu 2, and this was nu 3. Is that right? Yeah, nu 3. And so we would call this one the nu 2 plus nu 3 combination band. And whatever you see here is what you do to the vibrational frequencies. So if you see this label of that combination band, the 2 nu 2 plus nu 3, you take this 700 and you multiply by 2, and then you add in the 2300, and that's what you get. That's the total vibrational frequency. Now, this one is a little tricky to show, because how do you show twice the excitation in this motion and add in the asymmetric stretch? But all 3 of those things are happening at that frequency. So light somehow is able to come in and cause 3 wave functions to jump. Really 2 wave functions, one to jump 2 levels and one to jump up to its fundamental. So I don't understand that, and so I'm not expecting you to understand that. Okay, it's just the selection rules work out to where we can have some of these combination bands. So if combination bands kind of break your brain, that's okay. It breaks mine too. All right, because typically I can kind of understand a wave and a photon of light coming in and interacting with a single wave, but here it's interacting with the whole molecule, and it's causing excitation and multiple vibrations at once. So it's kind of strange. Yeah. So I don't understand that, but I do understand how to interpret it. It's just looking at the wave function and seeing multiple quantum excitations with 1 photon of light. So it's kind of strange. And so let's look at this support. Let's do the transition dipole moment integral. So this is going to be a large part of the test, is all of these different transition dipole moment integrals. So doing what's on this sheet right here is directly related to Wednesday. Okay, so everybody kind of wake yourselves up and we'll be ready to go. All right. So how would we support this? Well, we know that we're starting in the ground state for all of these. So 0, 0, 0. And then we have light coming in. We'll test this with Z polarized light. And then we have 0, 2, 1. That's our excited state for the, I'll go ahead and write it out here, the 2 nu 2 plus nu 3 combination band. So when we see that right there, we've got a 2 and a 3, so we have in order 1, 2, 3, so we have a 0 and a 1 because nothing has changed for that. We have a 2 in the second position because that's vibrational frequency 2. And then we have a 1 here because we have 1 unit in the vibrational frequency of 3. Pretty straightforward, okay? And this is the transition dipole moment integral. So remember, our intensity is going to be proportional to this integral squared. I'm going to close that door. Okay, and so we'll just work our way down through the symmetry species. We have the D infinity H character table for this molecule. And so we go and we find all of those species. Now, the vibrational frequencies here, let's go ahead and draw one here for, let's make this one nu 3. And that's going to go from A1G, okay, and nu 3 is A1U, and then A1G. Okay. And so that's how the potential energy surface goes up. It alternates between A1G. So this ground state is A1G, the V equals 0. It's A1G. Now what we're going to do for the 2 nu 2, let's draw one of those. A1G, and then what's the next one? It's E. Oops. And it's starting in 0. It's going up to 2. What we did, though, instead of jumping up to A1G, we went ahead and included the full symmetry because it's 2 units of that vibration. And so that 2 gives us 2 of those E1Us. Need to put that E1U there. So that's where we're getting all of these symmetries. We're going from A1G in nu 3 to A1U in nu 3. We're going from A1G in nu 2. We have 2 of those E motions excited, so we're going to go ahead and use that E1U twice here. And then there's no change for nu 1. I went ahead and just put it in there just to be complete. It's A1G, but A1G is not going to change anything. It's the top row. It's fully symmetric. It's just going to give you everything back. So it's like multiplying by 1. But I went ahead and put it in there just to show that everything is complete. And here's light. If you look at light in this character table, the Z polarized light would be A1U. So we've taken what we typically have 3 species in there, and now we've got, what is this, 3, 6, 7, 8 different symmetries. But we just use the direct product table and work them 2 at a time. Okay. And so we'll start from the right here. We have all of these A1Gs multiplied by each other. That's going to give us A1G. So that's pretty simple. And then A1U times A1G is returned back, because again, it's like multiplying by 1. Then we have the A1U times A1U, which the A1 times A1 gives A1, and then U times G gives us a G. I mean, U times U gives us a G. And here's where things get a little bit interesting. We have the E modes coming in, and they're doubly degenerate, so they have multiple pieces to their direct products. So A1G times E1U gives us E1U, and then we have this E1U times E1U gives us A1 plus A2 plus E. Now this it's kind of interesting. We have these are two dimensionals, two dimensions each. I'll say this. And when they're multiplied by each other, they give 4 dimensions. Okay, so this whole sum here you see a single dimensional row. So if you go to the character table, it's all 1s. You look under the E identity operator, it has a 1. You look under the A2, it also is a single dimensional row. But the E rows have a 2 under that identity. They're doubly dimensional. So you see there's 4 dimensions here. So we come in with 2 dimensions, multiplied by each other, we get 4 out. So 2 dimensions each. So 4 in, 4 out. Just something that I just want to show you because as a curiosity, it's kind of nice. Okay, now what do? We tend to have this sum here, and we want to take A1G times each term in that sum. And so the A1G times A1G gives A1G times A2G, and then times the E1G. So this is the integrand inside that Dirac notation. So this is an integral of 3 terms. It's a sum. And one of those terms is going to be non-zero. So that term that is A1G makes this non-zero, which means that this is an allowed combination band, which is a good thing because we see it in the spectrum. If this is not allowed, we've made a mistake because it's clearly allowed. The thing that this does give us, if we were to try to play around with all the different combinations that were allowed in CO2, we would find a lot of them that are allowed. And using symmetry, it tells us that there's so many that are allowed. But the problem is they may just have a really small intensity. So they may be buried down in the noise of that spectrum. We just don't see them. For some reason, this combination band has when you actually evaluate this integral, has a pretty large value. And so it has a pretty large intensity. So symmetry will tell us if the combination band is allowed or not, but it won't tell us the intensity. And so we have to go to experiment at least and find them. Okay. So let's look at this other combination band, the 101. So how would we write this? We would say that 3730 is nu 1 plus nu 3. You see the 1 and the 3 here. Okay, I guess we don't do that one. Do we do that one later? Sorry. Yeah, so I switched gears. Let's go ahead and do that one. Let's go back here to our symmetries. Nu 1 and nu 3. Okay, so we have nu 1 is A1G and nu 3 is A1U. Okay, and let's try this with Z polarized light. And I've left out nu 2. Okay, so okay. And so these are pretty simple here. A1G times A1G is A1G. A1U times A1G is A1U. And then those guys sort of cancel each other out and give A1G. And then this results in a single term. So we have the integral over all space of a function that's A1G, which is not equal to 0. Therefore, it's allowed. So we've shown that the combination band of nu 1 plus nu 3 is allowed by symmetry. And because we see it in the experimental spectrum, it has a large enough intensity to be detected. So those are the combination bands of CO2. But I thought that really wasn't a lot of practice, and so I switched over to acetonitrile because that spectrum had a lot of combination bands too and had some overtones. So let's look at acetonitrile. Here are the vibrational motions, the normal modes and frequencies for acetonitrile. This is a symmetric molecule, but it's not, and here's a word for you, centrosymmetric. It doesn't have an inversion center. Okay. And this was one of the questions on the homework that someone asked me kind of too late. I got it on Sunday. But this acetonitrile, no inversion center in C3V. therefore, we have Raman and IR active modes. So the same frequency here is active in the Raman and the IR. Yes?
So, when you're looking at those combination bands, you're going to where it says vibrational mode number, and that's where you're getting the character from? Like if it's non...
Yes, so this would be new 1 here, okay, and new 4. Okay? And the numbering has changed over the years. Okay, so you have to look it up. Like if you want to know the historical numbering for acetonitrile or you know, a given molecule, you actually have to see if it's been assigned in the literature. If it's been assigned in the literature, then you should use the assignment that has been published. So that way everybody's talking about the same labeling scheme. But if it hasn't been, and it's hard to prove a negative, right? But if it hasn't been published in the literature, then you use the Gaussian numbering, which is just from the lowest frequency to the highest frequency, regardless of symmetry. But notice this is not from low to high, regardless of symmetry. Look at this one. New 1 is the highest frequency one here. It's not actually not the highest, but it is a high frequency. And new 4 is this one. And then new 5 is actually the highest frequency, down to new 8. So what's going on here with this? Well, in the past, the only way you could really assign these peaks was to do a Raman polarization experiment where you could determine if it was in a symmetric mode, like an A1, or a perpendicular band, an E. So the scheme was, starting at the highest frequency, let's label all of the symmetric bands, all of the parallel bands, and high to low. And so all of the A1s here are grouped together, mode 1 through 4, and you see it decreases in frequency. And then we go back up for the E modes, the perpendicular bands at new 5, and label all of those high to low. So that was the original scheme for labeling, but it got really confusing because you couldn't tell if new 3 or new 4 or whatever was supposed to be, like in general, a low frequency or a high frequency, and it just depended on the symmetry of the mode. And so we've now kind of just switched to labeling them 1 up through 3n-6, starting at the lowest frequency, which I like better, because then the low quantum numbers are the low frequency ones, and the high quantum numbers are the high frequency ones. But you really can't tell. It depends upon if the molecule has been published or not. But notice how we don't have G's or U's here. No G or U. Those only exist if you have an inversion center. And these are both Raman and IR active because we don't have an inversion center. So if you have an inversion center, that's where that rule of mutual exclusion that was hinted at in the homework kicks in, where your Raman modes and your IR modes are totally separate. So you either have an IR active or Raman active peak. So let's look at some of the combination bands here. Here's a combination band, new 3 plus new 4 in acetonitrile. Here's a combination band, new 7 plus new 8. And then here's an overtone, 2 times new 8. Okay. And so here are our setups. We're not showing all 8 quantum numbers because that would really be crazy, too big. Okay, we're going to use Z polarized light for this. And so we have A1, 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 A1 all the way across. Okay, so we're pretty sure this is going to be allowed since everything's A1. Not a problem. A1 times A1 is A1, and it just keeps going down, all the way down, and we have an end result of A1. So that's not surprising that this one is allowed. Okay. Let's look at new 7 and new 8. Okay. So now we have some E's in here. So we have A1 and A1 for the ground states, A1 for Z polarized light, and then E and E for 7 and 8. So the first few are pretty straightforward, A1s times A1s, and then we have an A1 times an E. And so we didn't need the direct product table for any of this up to this point, okay? But when you get into E times E, you may not remember that. If you do all of these in the homework, or if you do all of these in the lecture by hand, that's a good way to kind of cement it in your brain. Even though it's tedious, having it go in your eyes, bounce around your head, and out your hand is a great way to kind of get it to stick. And so when you get to E times E, you need to go to the direct product table. But it's always this case that you have an A1 times an A, plus an A2 plus an E. So we come over here, we find this E here times an E there gives this result. And it's a sum. And so we end up with that sum of terms. And because it's a sum, we look in that sum, we see an A1, therefore it's not equal to 0. So it contains the top row. So that's the language I use. Of the C3V character table. And therefore it's not equal to 0. So this is an allowed transition. Okay, let's look at XY light for this. Okay, so this one I wanted to do because it gets, this is probably the most complicated one I think that you'll run into in terms of having 3 E terms multiplied by each other. Okay. And so the A1 times A1 is a piece of cake, A1 times E is easy. Then we need that direct product table. And so we do E times E, and that gives that sum of A1 plus A2 plus E. Now, what would we do on this? This is just like algebra, right? You just multiply through. So you take that E times A1 and write down the result, and then E times A2 and write down the result, and then E times E and write down the result. So just like you would multiply through in algebra, this is math as well. We're using letters all the time, but it's still math. And you have the same kind of basic rules to this. So E times A1, actually E times A1 is E. So this piece here is one of these E's right there. E times A2 is one of those E's right there. And then E times E gives us the sum. Does everybody see where everything came from? Okay. And then that sum contains the top row, so therefore this is not equal to 0. So that also lends support to this combination band being so intense in the infrared spectrum, is because both Z-polarized light and XY polarized light will cause it to occur. And so you have 3 ways for this absorption to occur. And so that just makes its absorption's peak higher. So let's go ahead and do a Kahoot on this.